And let's go into interpreter.run. This is the core of everything. So what it does, it takes the contract code and it executes it byte by byte. And here we are increasing the depth, and then we are checking if the depth, doesn't exceed 1024. And we are using defer function. So after everything is run in this function, we are decreasing it by 1, because that means that we are already out of this current call depth. And if this is read-only flag, remember, if we are using static call, we are setting the flag. And also this applies to the case where, for example, you have some view function that is called by static call, and then this function calls something via normal call. Normally Solidity doesn't allow you for that, but of course you can, work around that by using an interface that you declare, for example, as view only. So the static call will be used, and then this contract may not be view only, and it may call some other contracts. However, still in the same case, if this is set as read only, all the calls inside will also have to obey these read only rules. Then we reset the return data. Remember, we have to have clean state before every transaction is being run. And if the code is not existent, we return nil and nil. This means that there is no error. That means that we are not returning any return value that will be reused by other contract. And next we have current opcode. Each time that we are in this run, that means each time that we are calling some other contract or creating contract, we are receiving new memory, a new stack, and new call context is being created for us. We start with process counter of 0 and all the other useful elements. Set input, which is our call data, and we'll just log something in case that we need that. And this is actually the main loop. This is the for loop, endless for loop. This is endless because you never know how much code you will use. For let's say that your contract is like only 10 opcodes, but maybe it just constantly calls itself, or use jumps to have an infinite loop. So you cannot tell otherwise how long the loop will run. Next, we get current operation at this process counter. We are looking it up into operation table. We will go to that in a moment. We are calculating constant gas for operation. Here we are checking our stack, so how much stack we have currently, and if it either underflows or overflows. Next we use the constant gas that has to be used for this operation. If this is not successful, that means that false is being returned. We are reverting with error out of gas. And also, if operation has some dynamic gas, we are calculating it here. We are using memory size because all the dynamics costs that are, on different operations are usually dependent on the size of the memory. Here we are applying the dynamic gas costs and adding it here. And of course, again, we are using this gas. If this is debug, we are logging stuff, and we resize if required, because remember that memory is just a byte array. So it starts really small and then you just resize it, to fill different needs. Next, we are calling execute on this operation. Of course, different opcodes have the execute function defined differently. And we check if it reverted. If it did, we are breaking, and we are then increasing the process counter. And the loop continues to run all the opcodes that it has to run. Then we check if this is stop. So if we use the stop opcode, that just means that error, really there was no error. We are reverting with this error inside, you know, just for having consistent behavior. But we check it here. If this is stop, we are just removing the error because it's not really error. Yep, and finally, after last opcode, this is usually either stop or revert or return. There will be some byte array that is being returned, some memory copied to return, and we are using it here. So now, if we know how it looks, now let's go into the real opcodes. Before that, I want to show you that we have the Jumptable. Jumptable is just a mapping between opcode code, for example 0x31, and the real function that has to be run on it. So we have this Jumptable, and depending on the version, we are using different instruction sets. So let's go and see how the most recent one, cancon instruction set, is being defined. Okay, this is cancon instruction set. So you see that we are reusing everything that Shanghai instruction set has, and we are enabling EIPs that are in this particular hard fork. For example, you can see that we have the blob hash here, new operation that execute has this op blob hash, and we can really go here inside and see how each of the opcodes is being really implemented. All the opcodes has the same input. So first, in case of in this particular blob hash opcode, we are using a single stack element, and in case of blob hash, we are taking one stack element and we are returning nothing to the stack. So in this case, we can see that blob hash at minimum takes one element and returns one element to the stack, and maximally it takes the same. And this is implemented really simply, and every opcode is really implemented like that. So because we are getting one element from the stack and then we are putting it back, we are using peek in go-ethereum. We may have either peek or pop. The difference between them is peek just returns first element without doing anything with it, and pop returns it and deletes it. So in this case, we are doing some checks and returning index of blob hash. So you can see the index is gathered here, and then because we are calling setBytes32, we are reusing the same stack element, and we are clearing it if it's not being found. And very similar situation is done for each of the opcode. Maybe, you know, go through some of the exemplary opcodes. Operation self-balance gets balance from StateDB and pushes one element to the stack. For example, here you can see that blob hash takes 3 constant gas, and it takes it always, and we have different jump tables being used. This is interesting because, for example, op self-destruct, we have 2 op self-destructs, normal op self-destruct and new op self-destruct, which was enabled in EIP 6780. For example, stop does nothing, just return this stop token that we spoke about. Undefined is similar, but it returns error invalid opcode. In this case, as I remember, because this is not revert, it will burn all the gas possible. And op revert, we already also saw that. If this is error execution reverted, all the gas is not being burned. And the return data that we return here, we are just setting it to the memory pointer that we set. So if we have revert opcode, we are taking 2 stack elements, offset and size, and we are consuming both of them. And the same, you can see here, we have offset and size, and we are taking it from, popping it from stack, Then we are getting the memory with this specific offset and size, and this is our return value. So I hope that now it makes more sense on how it works under the hood. And then, just to be on safe side, we are verifying if this instruction set is complete, if memory size for every operation is set, and dynamic cost is set, and everything is fine, really. And maybe let's go into how dynamic gas is being executed. Oh, and this is a bit tricky because this variable gas self-destruct EIP 3529 is returned from make self-destruct gas function, which is a bit strange, but it returned gas func. And this gas func is actually declaration of function. So we are returning the function that we just created it. And because of that, we can then use it as normal variable. So in this case, we are checking the address. And if address is not in access list, we add it to access list, and we are applying cold account access cost, which is 2600. And then if actually we are in our self-destruct, if we are sending it to address that doesn't exist, we are applying additionally 25,000 gas for that. And finally, we are adding refund. So yeah, this is basically all concerning create. Call is actually very similar. We are also landing here in interpreter, and we are also calling this run function. So maybe I will show it now. Okay, so we went through this path of evm.create. And here we have our return. Again, in this case, our return is the contract code, gas that is being remaining, that is used for refund for the user in case of maybe any error occurred. And we skip the contract address here because it's not required. Otherwise, we are using EVM call with the message data, gas remaining value, and all the other stuff. So the call is quite intuitive. Here we are having the tracer. We are checking if the call depth is not over 1024. We are checking if the user actually has enough funds to send it to anyone others. Again, we are performing snapshot here. And interesting, we are checking if the address that we are calling is a precompile. And you can see here, precompiles is just a list of addresses that have precompiles. And we can see here, we have bytes to address under address 1, we have EC recover, in 2 we have SHA, and all the others, and here we have data copy. So we are checking if the given address that we are calling is precompile, which will be required later. Then if the address doesn't exist and it's not a precompile, because remember that precompiles are not implemented as a smart contract, they're implemented directly in chain, and we will look at implementation here of some of the precompiles. So if it's not a precompile and there is 0 value, we are just doing nothing. We are returning the gas. Then we are transferring the funds before we actually call it. And next, if this is precompile, we are not even going into this part that calls a smart contracts and interprets the code. We are calling run precompiled contract. Then you can see that we check, all the gas that we have and everything, and call run on it. So maybe we can see, for example, how EC recover works. So as I said, EC recover is precompiled, which means that is implemented directly into go-ethereum and all the other implementation of EVM. So yeah, what more can I say? The address of it is 0, however, it has its own logic. And if this is not a precompile and this is smart contract, we are getting its code. If code is 0, we are doing nothing. And more importantly, the error is nil. So remember, if you are doing some low-level call and it succeeds, it may mean that the contract is not existing, because if it's not existing, the error is nil. So you should be aware of that. Otherwise, we are creating reference to this contract. We are setting code for this call. And again, the same situation, we are calling EVM interpreter.run. So the same that happened with create. But the difference is that on create, we didn't get the code from StateDB. We were using the code that was passed in the call data. After running it, we look how much gas we have left. And if any kind of error happened here, we are reverting to snapshot. In case that this is not error execution reverted, we are setting gas left to 0. And that's all concerning call. So we might end here, but I want to show you some things that I find interesting concerning gas. So here we have normal call and we have also call code. They are all very similar to each other, but I won't discuss call code because this is deprecated for a long time. Delegate call is interesting. The main difference, and basically the only difference that is there between call and delegate call, is this line, really. In case of call, we have just this new contract, and here we have new contract as delegate. And what as delegate function does, that's all. That's all it does. So technically, delegate call just change the message sender to parent and changes the message value to the parent value. But this is not really intuitive, at least for me. So I like to think about it, and this is what I already mentioned in some of the episodes before. I like to think about delegate call as just borrowing the code logic for yourself. So you have contract A, and there is some function on the contract B that you want to call as if it was your function. So if you are using delegate call, you are using this function of contract B, but in a way as if it was your own function that you run on yourself. But technically, you can, if this is easier for you, you can think about it that you are getting the value and caller address from your parent. So if you are in contract A, you are calling contract B, and that contract B calls, delegate calls contract C. The contract B will, in contract C, message sender will be contract A, and message value will be the value that is being sent from contract A to contract B. That's why you have to make sure how do you do delegate call, because you cannot really send value with delegate call. If you look at the difference here, you can see that in call, we are taking value that we want to send with this call. In case of delegate call, there is no value. You cannot send value there. Like, the value is taken from your parent context. You have to watch how, on the value that you try to register when we are using delegate call. And next, everything is the same. We set call, we run the interpreter with the contract code, revert if needed, and then we have static call, which is super similar. Again, one intuitive thing is that they do snapshot, which is not really required because any change to the state will not be effective. But they mention that static call is considered a touch. So if you use static call to call any address, the address is considered to be warmed. So they take snapshot here and then they are adding balance, which is a bit strange, but the balance that they add really is initialized with 0. And again, this is precompile. We are running precompile contract. And the only difference here, the main difference is that we have here flag read only set to true. And I think that's really it. Maybe we can quickly just go through other interesting opcode implementations. So, okay, you can see here that, for example, op add, we are popping one element and we are picking other. We are picking other because we will reuse that, because add takes 2 elements from the stack and returns 1 element. So the second element we are using to return addition of 2. We have lower than, so if this is lower than the other one, we are setting 1 here in Uint256. So this is actually Uint256 implementation, so I will not go deep into that. This is outside of the scope of EVM. go-ethereum just uses this library, Uint256. Next we have, like, for example, address and balance. So you can see here that we are just reading from the different places. Here we are reading address from our current scope. So from our current contract. In balance, we are using stateDB to read current balance. In origin, the same. In we are using EVM origin that is set, and similarly to others. Call data copy is interesting because we are copying call data to memory, and we are first taking 3 elements from it, and then we are copying it to memory. In case of jump, what we are really doing, we are taking the process counter and we are overriding it to different value. Of course, if this is a valid jump destination. So if the place that we want to jump to is jump dest opcode, otherwise we are reverting with error invalid jump. Sorry, we are actually throwing an error that will just revert all the execution. Again, like jump dest is really no op because we are using this validation that is done before, and op create because smart contract can be either created via the transaction type create in case that the transaction is being sent to nil recipient, null value, then it's considered as smart contract create. Or you can use a create opcode, and this is actually used here. You can see that we are in this case only passing 63 of 64 of gas here. The code is reused from what we saw before. We are using evm.create, which in turn create the others and then uses interpreter to run the code. Then we are pushing item on the stack based on the return error, and we are calling refund gas. So actually we are here adding back the gas that user didn't use. So remember, at first we are buying gas limit times gas price, so we are taking everything, and then if we did not use anything, we are getting a refund of unused gas. Then we have opcode 2, which is super similar. We are just not using create but create 2, and as we saw before, the difference between them is just how we derive address between them, and everything else is the same. Operation call, same as we saw before. We are using EVM that call. We are taking all the importance parameters from the stack. Again, as we create, we are refunding gas that was not used afterwards. And to be honest, although on this level, on level of the opcode, the delegate call, call code, and static call are super similar to each other. Here we are making logs, so we are adding it to stateDB. And this is interesting because you can see here that we have only op push 1, and we do not have push 2, push 3. That's because it will be a lot of repetitive work to create all those instructions, like 33 instructions for push. We have push 0 to push 32. So how they do that, they are having this function make push, and in Jumptable they are using make push, and you can see that they are using it 32 times in Jumptable. And that really concludes how EVM operates. We went through all the most important workings of it, and I hope that by now, by going through whole EVM programming course and this video, you have now way better understanding of how EVM works under the hood. That's all for today, and see you in the next one.